In this session, we're going to discuss a little bit some basic thermal effects on materials and structures. We're just going to concentrate on longitudinal effects on a structural bar. So the basic equation is this one here. The strain induced by a change in temperature, it's going to be equal to the change in temperature times a thermal expansion coefficient. Under wide range of temperatures, this thermal coefficient is constant. But if the temperature goes really high, then this alpha becomes actually a function of temperature. But in this discussion, let's just work with alpha equal to a constant, and let's just operate under the assumption that the temperature change is within the elastic recoverable range. Here are some values for different materials like aluminum, steel, copper, concrete, and plastics. These materials have different thermal expansion coefficients ranging from around 6 for concrete, a little bit higher for steel, all the way to about 50 for plastics. So why is it important to understand the effects of temperature on structures? Well, because the strain caused by the change in temperature will cause an elongation of the material, a change in volume. So if the temperature goes up, the material will expand. If it goes down, the material will shrink. And in the case of a bar, the elongation, in addition to creating a deformation, it could also create thermal stresses if the bar is restrained. Let me show you an example of that and how would you do those calculations. So let's say we have a bar which is restrained only at one end. Let's say it has a length of 36 inches and is a solid circular bar of 2 inches in diameter, and it is made out of aluminum. So say this bar experiences a change in temperature of 100 degrees Fahrenheit. And I must say that these values that are given here are all multiplied by 10 to the minus 6. Right? And this is strain per degree Fahrenheit. So if we use this formula, we will obtain that the temperature-induced strain is going to be 100 degrees Fahrenheit multiplied times 12.8 times 10 to the minus 6 per degree Fahrenheit. So that will give us a total thermal strain of 0.00128. Right? And obviously this is deformation per unit length, so it has no units per se, but we could say it's inches per inch, right? And so this means that the total thermal expansion at this end, due to a positive change in temperature of 100 degrees, is going to be strain times length equals 0.0128 times 36 inches, and that's going to be 0.046 inches. So that is the total elongation that this bar is going to experience at that end due to a change of temperature of 100 degrees. Clearly that occurs uniformly throughout the length, so it's all elongating up to this point, right? Now what would happen if this bar was now restrained at both ends, and you still had a change in temperature? Now, this restraint would have to include a restraining force that would obviously have to be acting equal and opposite here, that would prevent this elongation from happening. And the bar would actually be subjected to compression due to the temperature increase, because it wants to expand, but it can't because it's restrained. So how do we calculate this restraining force? Well, if we go back to our basic formula for deformation, what we're basically saying is that this force is eliminating this deformation back to its original undeformed position. So we basically have PL over AE would have to equal the temperature induced deformation. So we know that, we know length, we know A, we know E, and so we can find R. So from here, the restraining force would be delta temperature times AE over L, which, by the way, this here is the stiffness of the bar, AE over L. So what this tells you is that the restraining force is going to be larger depending on how stiff the bar is. And that makes sense. In this case, with a diameter of 2 inches, that gives you a cross-sectional area of 3.146, right? Which is pi diameter squared divided by 4. And with the elastic modulus of aluminum being 10 times 10 to the 6 psi, and the length being 36 inches, if you do the multiplication, you get a total restraining force of 40,212 pounds, which is a large force. So as you can see, the forces due to temperature restraint could be relatively large. If you actually take this force to obtain the stress, you obtain a stress of approximately 12.8 KSI, which is not small at all, especially considering the fact that for a typical aluminum material like T6061, the yielding stress is in the order of 40 KSI, so this is about a third of the yielding stress. So a considerable amount of stress could occur due to significant changes in temperature in a bar. Aluminum is a very popular material, for example, in the aircraft industry. Aluminum 6061 is used a lot in wings and fuselage, is easy to weld, is relatively light, and has very high strength. And these types of structures undergo a lot of changes in temperature, especially as they go up and down and experience different environmental conditions in the atmosphere. So it's very important to consider these temperature effects. The same thing happens in civil structures like bridges that are subjected to thermal expansions due to the changes that occur in temperature throughout the year, and those expansions have to be accommodated somehow so that the bridge can move without creating additional stress. Fortunately, and I want to end this session just by pointing this out, you can see here the case of civil engineering. This is a very important fact, that steel and concrete have a very similar thermal expansion coefficient. That is very important because in the case of reinforced concrete, you have these two materials combined, like in a column where you have steel bars, and if those thermal expansion coefficients were very different, reinforced concrete structures would suffer tremendously due to changes in temperature, which could make them really unfit for use if this difference is too high. And we're going to talk about that in a future session. What are the thermal strains and stresses induced when you have two materials combined and they want to expand? Again, fortunately, steel and concrete have very similar thermal expansion coefficients, and so they can be used together to create reinforced concrete.